Hey, let's take a look at section 2.1, linear functions. So yeah, in chapter 1, we kind of started talking about functions in general, and now we're going to get really specific. So we're going to talk about linear functions in this video. Okay, so linear, right? We see the word, we've seen this word before. The thing we should be looking at is the word line, right? We're going to be talking about lines. Okay, so we start out with a definition. So we're going to build everything from this definition. So the slope of m, or excuse me, the slope m of the line containing these 2 points is, we're going to have slope. So this is change in y over change in x. In the literature and textbooks, we might see something like this. If we're going to go take calculus, we'll see something like this. This delta, the letter delta. This means change. Okay, so this is, sometimes we see this as rise over run, but the thing that we want is the math version of this, right? The mathy version of this. So it's the difference, the change in y. So we got the difference in the y coordinates, and we're going to divide by the difference in the x coordinates. So when we're looking at a picture here, maybe I've got my point x sub 1, y sub 1 here, and maybe I've got my point x sub 0, y sub 0 here. So we've got a line that contains these points, and here is how we define slope. So great, we got slope. We got a nice beautiful definition here. Okay, we'll see this in a couple of different contexts. We ought to maybe tuck away in the back of our head for now that this is going to be a rate of change. So when we're going, from right to or left to right, we're going to say that the slope of a line is the rate of change, right? The change, how many units do I go up for how many units do I go to the right? Or, how many units to the right do I go for each unit up? We could think about it in either way. So we'll take a look at some in context later. Let's check out an example. So let's have the point 3, 2 and negative 2. Let's have a fraction in there. So find the slope. Find slope. Okay, so we got 2 points here. And we're going to do what we've done before in these sorts of contexts. We're just going to call one of these x sub 0, y sub 0. We saw this with distance. We saw this with midpoint, right? We're just going to give, we're going to give these 2 ordered pairs those subscripts. And then we're just going to plop it on in there, right? So we got y sub 1. Let me just write this. So our slope here, we've got y sub 1, so that's 1/2, minus y sub 2, which is 2, divide by x sub 1 minus x sub 0, so that's 3. I think I might have said 2 there. I meant 0. Okay, so great. We can do this subtraction here, right? In the denominator, that one's easy. We got minus 5. So then we have what? 1/2 minus 2. So 2, we know that that's 4/2. So we've got negative 3/2 over 5, which we've got negative 3/2 times 1/5. So we've got 3 over 10. All right, there we go. We got a beautiful slope here for between these 2 points. So the thing we need to be careful about, and the thing that we'll usually make mistakes with, is that we need to do these in the right order, right? We've got to make sure we keep our subscripts straight. So as long as we're doing these in the same order, we're going to get the same value, right? So to put that another way, we might ask ourselves the question, does it matter which order I put these in, right? Maybe I want to call that one x sub 1, y sub 1. I want to call this x sub 0, y sub 0. Maybe I want to do that. And we might say, does that matter? Well, let's look at this example and show ourselves that it doesn't. So we got y sub 1 is 2. Y sub 0 now would be 1/2. And then I would have 3 minus negative 2. So we got 2 minus 1/2. Well, that's still 4/2, right? So we got 3/2 over 5. And then we do get the same value. Notice what happened though, right? And when we switched the order of both of these, the sign changed, right? So instead of having a negative over a negative, we had a positive over a positive, right? Okay, great. So moral of the story, doesn't matter which order we find the slope, excuse me, doesn't matter which order we notate this, just that the subscripts are consistent, right? So be careful with that. All right, great. We can find slopes. Okay, so we can recall equations of vertical and horizontal lines. So this was from, I think maybe one of the first couple sections we did, right? Vertical lines always have the equation that looks like this. Always, right? And we can draw a picture. Hey, there's A, and my vertical line would be this, right? And if we wanted to plot points for this to say, how do I draw this? Pick any X you want, or excuse me, pick any Y that you want, and X is always going to be A. So, we get a point here, point here, point here, everywhere, right? Horizontal lines, this is similar. We had Y equal B, and we have, there's B right there. So similarly, right, choose any X value, and it's going to be on that line, right, because the Y coordinate's B. Okay, so we recall this. That is kind of going to be important for you in a few of these exercises. All right, the point slope form of a line with slope m containing point x sub 0, y sub 0 is the equation. So we're going to have a nice equation here, and at the end of the day, we're going to have a little formula. It's going to look like this. It's going to look like that. Super. It's not really the intention to just memorize this for the sake of memorization. So let's look at how we come to this. And we said before, everything's going to get built from slope, and it does. Maybe we can look at this and see, I've got slope here, and if I solved that for m, well, we would divide by this stuff. Well, that's going backwards, so let's go forward. So the point slope of a line with slope m containing the point blah, this one is the equation. Maybe we put a question mark for now. So let's say xy is on the line. Okay, well, if I've got a point that's on the line that is not this one, by virtue of this thing being a line, the slope between our point x sub 0, y sub 0 that we're given, and the point that we supposed is on there, must be m, right? And then we have a nice little formula for this, right? It's the change in the y coordinate divided by the change in the x coordinate, right? So we got the difference between our x's and y's here, right? This is just the definition of slope. And then, if we would take this and write it without the fractions, well, we're going to multiply by x minus x sub 0 on both sides. And, right, there we have it. So just, rearranged thus. Okay, so great. We've got a nice little formula here. And the good thing is here, this is just slope. It's just the definition of slope, just rearranged, right? Well, this is going to be useful for us when we want to write equations of lines. So let's write an equation of a line through maybe the point 2, let's have a square root of 3. Let's have that negative with maybe slope 2. Well, all we do is what we've done before, right? We're going to call this x sub 0, y sub 0, right? Because we have a point on the line and we have a slope. It's m, right? Write that. Okay, so at that point, well, we're just going to plop these into our nice equation here, right? We got y minus y sub 0 equal m, so that's 2, and then x minus x sub 0, and that's it. Well, we should probably get rid of any extra grouping symbols that we don't need, right? Or any extra notation, right? We don't need that. So if we're specifically asked for point slope form, that would be it in this case, and we would write that. Let's do this one more time. So let's find, maybe we can do it backwards. So let's find, well, let's not do it backwards just yet. Let's do the same thing we just did here. Find equation of a line through the point 3, 7, and 1/2, let's say 9. Okay, so now we're given a point and another point, right? We're not given the slope, but we can sure find it, right? If we want to do write our equation in that form, we need the slope and we need a point on the line. So we need m, right? We need the slope. So our slope we can find by just using that nice little formula, right? We want the change in y, so we got 9 minus 7, and then the change in x. So we would have 1/2 minus 3. Just to be extra clear about that, again, we can call that x sub 0, y sub 0, and we can call that x sub 1, y sub 1, and we can plop those into our nice little formula that we had for slope, and then yeah, compute this, which will be 9 minus 7, we got 2. 3, we know that that's 6 halves, so we have negative 5 halves. So this is negative 4/5. Okay, so that is super. Now we have our slope, right? And we can finish up. We got y minus y1. Well, hold on a minute. Which one of these points do we want to use? Do we want to use this one or this one? And a natural question would be, does it matter? Well, they're both on the line, right? So if they're both on the line, they're both going to make it a true statement if I put them in there. So long story short, you can use either one. We want to use probably the one that's easier looking. So if I were you, I would choose the one maybe with the integer coordinates, right? Because that's somehow easier for us to think about. Okay, and that's it. Now again, we definitely could have used this point instead, but it looks nicer written like this. Okay, great. So if we're given a slope and a point, we can do this. Or if we're given 2 points, we can do this, right? Just construct the slope first. All right, slope intercept form of a line. So if we have our nice guy here, right, we know that this is slope intercept form, or excuse me, point slope form. Now if we solve for y, we can do this, right? We would just add y sub 0 to both sides. So if we add y sub 0 to both sides, and maybe we can multiply this through on the way, right? So we would have mx minus mx sub 0 plus y sub 0. Okay, so this doesn't really look like what we are probably familiar with here. Oops. So we can maybe think about this using y-intercept, right? So what's the y-intercept here? So if we're finding y-intercepts, we recall how we do this, right? We're going to set x equals 0, solve for y. So we did this in a previous section, right? So if I put x equals 0, that's just this one, right? So we're going to have y equal that stuff. So this is just some number, this is fixed, right? That's just a constant. And so are these coordinates here, x sub 0, y sub 0. Remember, this was the point that was on our line. So this is just some number, and we're going to call this b, right? So we can rewrite this as y equal mx plus b, where this b here is just that mess of junk, right? We can approach this in a slightly different way, where we maybe start with something different, and we don't solve for y. So let's say I just want to know what is my equation if these 2 points are on my graph. So we're going to use m equals, well, just m and then x sub 0, y sub 0 equal the point 0, b. So if we put this in here, we've got y equal, or excuse me, y minus our y sub 0 is b, and then we've got m, and then we've got x minus, well, 0. Okay, well then that's just x. And then if I solve that guy for y, right, add that b to both sides, we get the same thing, right? So, okay, good. So this is slope-intercept form of a line. We can think about it in both of those ways we just presented there. So this form of a line is not going to be terribly useful for us to write equations of lines. This is going to be useful for us to find information usually. So let's look at an example real quick here. So if I have y equal 2x minus 5, just immediately we can look at this and we can say, oh, okay, slope is 2, and this is our y-intercept. So that corresponds to the point 0, negative 5, right? That's our y-intercept. Okay, great. So that's usually more useful for us when we're writing equations of lines. Now, no. When we're getting information, we want information. So let's take a look at something that's slightly different, but it's kind of the same. So maybe if I have 3x minus 5y equals 2. So let's find m and y-intercept. Okay, so we can do the y-intercept the way we usually do it, which would be to just put x equals 0 and solve for y. And we can see right away it's going to be negative 2 over 5. But let's do this in a slightly different way. Let's rewrite in, or maybe as. Okay, so I can take this guy and we can solve this for y. So we can move the 3x over to the other side, right? Subtract it from both sides. And then we can divide everything by negative 5. So we got y equal negative 3 divided by negative 5. So we're going to have 3/5. And then 2 divided by negative 5 would be minus 2/5. So now right away we say our slope is 3/5 and our y-intercept is negative 2/5. Or we can, give the ordered pair, right? So depending on the context, we might want one or the other of those things. Okay, so that's what that is useful for. So we absolutely can use this to write equations of lines. And if we're given certain information, it's easier, right? If we're given the y-intercept, if we're given the slope, that's easier to use this. But if we're just given 2 points, it's going to be easier to use the other form first to find our equation. Okay, good. Okay, so now we've got a linear function. So linear functions, we're just going to replace the y with our function notation. So any function that looks like this, we're going to call it a linear function, and it's the graph is a line with slope m and y-intercept b. The domain, we can say what the domain of any linear function is. It's all the real numbers, isn't it? So any linear function, I can multiply any number by m. If I have some real number here, I can multiply anything by that number, and I get one thing, right? And if I add some number, I'm going to get one thing. So domain is all the real numbers here. Constant function. So recall from what a graph of a function looks like, if it's constant, it's going to have to look like this, right? It's a horizontal line. Well, we know already that horizontal lines have this form, right? Y equal b, and we did this a couple pages up, or a couple screens up. All right, domain of any constant function. Well, it's that. So okay, so these are just things that sort of fall out, and really we're just using function notation here, and then nothing really new is being added. Okay, we've got an application problem. Super. So the number X of video game systems sold in a week is related to the price P in dollars of each system. Okay. When the price was $220, 20 game systems were sold in a week. when the systems went on sale the following week, the 40 systems were sold at $190 per system. Okay. So we want to write a linear function that models the situation. Use x, the weekly sales x is the independent variable. So if my x is going to be the independent variable, then the dependent variable is going to be the price, P. So we might as well write x comma P of x. These are going to be what our ordered pairs look like. Okay, so we want, well, don't we have, if we want a linear function, if we want to write a linear equation, I need two ordered pairs, right? And we have them. So if my ordered pairs are of this form where we have x is our number of units sold and P of x is the price corresponding to that, well, we've got our two ordered pairs right here and here, don't we? So we want the number sold paired with, so the number sold paired with the price per unit. And our other is going to be the number sold and the price per unit. Okay, so we can find our slope now. It's just going to be the change in y over change in x, right? So we got 190 minus 220 over 40 minus 20. Okay, and we can do the little computation here. Looks like we got negative 30 over 20. So this was negative 3 over 2. Okay, great. We found our slope. How wonderful. Now we can, we could either jump right to writing, my function is to be P of x equal blah, blah, blah. We can jump right there, but I would argue that it is easier for us to first write this in slope-intercept form here. That is not slope-intercept form. This is point-slope form, excuse me. So, right, because we have our slope, that's m, and we have points that belong, doesn't matter which one we use. So we can write y minus whichever one you want. I'm going to choose the one on the left because it comes first, right? Then we got the slope, negative 3 halves times x minus x sub 1 would be 20 there. Okay. And now I want to write it like this, right, with the function notation. So we're just going to solve this for y. So I'm going to add that 220, and we might as well multiply this through at the same step, right? So we're going to have negative 3 halves x, and then what? We've got negative 3 halves times negative 20, so we're going to have plus 30, right? We can do that multiplication there, right? Divide by 2, we get 10. Multiply by 3, we get 30. And then add the 220, right? Because that had to come over from the other side. So we can write it as y equal negative 3 halves plus 250. And of course, we want to write it with our nice little function notation, so we can replace that with P of x. Okay, so here is the price for however many units you sell. I forgot the x there, so there it is. All right, super. I would advise us to go here first, but we could put this in a different color. We could do this in a different way, right? I could write P of x equal, I know it's got to be mx plus b, right? Because this is a linear function. Any linear function always looks the same. It always has to look like this, no matter what. Well, I have 3 halves, so I can say P of x has to be negative 3 over 2 x plus b. And then we might say, well, what do I do now? Well, we need this b, right? So here's where we might get stuck if we're going this route. So to get over the hump here, we've got to recognize that we've got ordered pairs here, 20, 220. What this tells us is that f of 20 has to be 220. So I can use this fact and plug it in here to find B. So P, I guess I should have written an F, not an F, but a P. So P of 20 has to be 220. Well, if I put 20 through my function, it looks like this. And now we can take this and solve for B. Okay, so we can do that pretty quickly, right? 220 equals 20 divided by 2. That is 10 times 3 would be negative, times negative 3 would be negative 30 plus B, and then B is 220 plus 30, so 250. And now we would take this value of B, plug it right back in there, and we'd see, hey, we get the same thing. So there's two different paths to get to the same result. I would argue that the one on the left was a little bit easier conceptually, I guess, but we can equally do the one on the right. So great. Okay, average rate of change. So let's take a look at something. We kind of glossed over the fact that we're going to be talking about rates of change. So let's look at slope here for a second on a line. So if I got a point here and a point here, the slope of this line is how far I go to the right. It relates these two things, right? I'm going to do my change in y over my change in x, right? So this is the rate of change, right? How far do I go up for each unit I go to the right? For any lines, this is constant, right? The rate of change of a line is constant. But if we look at a curve, the rate of change is not constant, right? So if we think about the rate of change of a curve, we might say, all right, what's the rate of change here, or here, or here at any point? Well, we would be drawing, thinking about where the graph is going. I would probably draw one that looks like this, a line. I'd say, all right, the slope of the graph right there is the slope of that line. And right here, the slope of that is the slope of that line. And, the same thing, right? We can draw a line that kind of encapsulates what's happening at that instant of x, right? When we go through from left to right, we can kind of see that happening. We don't want to talk about this in too spacey of a way, but you'll talk about this more in calculus maybe. The big idea that we want to say, or we want to bring forward here, is that we can have instantaneous rate of change, so the rate of change like at a point, or we can talk about average rate of change. So if I want to take from A to B, I want to say what's the average rate of change, we're just going to find the slope between these 2 points. Draw that in a different color. That didn't really look like all that straight of a line. So average rate of change of f over the interval a to b is defined as, well, let's write it in words, the slope of the line containing a comma f of a and b comma f of b. So here it is in words, or we could write it in symbols, right? So average rate of change is, well, it's the slope between these 2 points, right? So it's the change in the y variable divided by the change in the x variable. Okay, so yeah, here's a for your information. We use this, a secant line, a line that connects 2 points on a function is called a secant line. You might see this word later, or maybe you've already seen this word in a trigonometry sort of situation, or a geometry sort of situation. We might have seen this word before, and maybe we'll talk about that in a later course. Who knows? Anyway, let's look at an example here. So if I want the average rate of change, let's say the function let's do something. Yeah, we can maybe do a little bit of review as well. Let's go 2 to 4. And do we use closed? We do. Okay, so we just want average rate of change of f on this interval. So just in plain words, we want the slope between these 2 points, 2 comma f of 2 and 4 comma f of 4. Okay, so let's find that slope. What we might want to do first is find these 2 function values. That'd probably make our lives much easier, right? So f of 2, we can find that real quick. We're just going to put a 2 in for x. And we can compute this, right? That's 0. Square is still 0, and then we got 1. So then f of 4, we can find this one. So we've got, we put a 4 in place of x in our function f. Okay, so now we got 2 squared, which is 4, plus 1 will give us 5. So now our ordered pairs here become 2, 1, and 4, 5. And now we can find the slope of this pretty quickly, right? So average rate of change is f of b. Let me just write what our nice little notation tells us to write. So we just found this, right? We found f of b, which would correspond to our second point here, so f of 4. So we would have 5 minus, okay, so f, let me just replace these with what we have in our problem, just so there's no confusion here. Okay, so f of 4, we know that's 5. F of 2, we know that's 1. And then divide by the change in the x value. So we've got 4 over 2, which is 2. All right, so the average rate of change of this function over this interval here, over this function over this interval is 2. So let's think about this in terms of what we talked about in the last couple of sections. Okay, so now we found the average rate of change here, and that's great. Now, if we were to draw a picture of this, we can think about this with transformations, right? Where we would have the transformation of our x square function. We would go, first thing would be go right 2 units, and then we would go up 1 unit. So we could think about, that parabola. It would be right 2 units, up 1 unit. So it'd be like up in here somewhere. So what we've done is we've found the slope between these 2 points, right? And we could draw a better sketch if we want to. We just kind of wanted to relate this to what we've been doing, and the graph is useful, I guess, when we're visualizing this stuff, what it is that we're actually doing, right? So average rate of change, this is slope between 2 points on a function. Okay, super. Well, that's it for section 2.1, linear functions. We'll talk about this stuff more in more detail in future sections, but yeah, for now we've got a good start. So let me know if you have any questions about anything here. Otherwise, yeah, have a great rest of your day. Thanks for watching the video.